So for today, we're going to be now looking. So imagine we've now run our eye tracking experiment. Last week, not last 2 weeks ago, you all had a sort of the first hands-on on the eye tracker, seeing how you actually use it. So imagine that we've actually now run an experiment, and we have that glorious data file which has our eye tracking data in. How do we go about analyzing it? Well, there are many different ways of actually analyzing eye tracking data. Um, the easiest is the one I'm going to show you today, and that's to actually use software which is designed specifically for analyzing these data files. Remember, these data files tend to be quite large. So if you're running upstairs, the eye tracker is sampling at 1,000 hertz. That's 1,000 lines of data per second, per trial, per subject. So it's very easy to start getting millions of lines of data. In fact, it's so big that Excel will not actually open. If you've got an experiment trial that lasts 5 seconds, you've got 240 trials, which would be a sort of a normal experiment. You multiply that by about 20 or 30 subjects. Excel will not open up the data file. It's just too big. It'll actually only open up the first 5 million data samples, and then it'll stop and it'll say it's out of memory. The file's too big. So that means that you have to use other means. And there are different means. So if you can program, you know how to use R or MATLAB, you can import those data files into R and MATLAB and analyze them that way. The other way of doing that, of analyzing data, is to use this Dataviewer. This is SR Research's version of an analysis package. Most eye tracking companies will have something that's equivalent that comes with their eye tracker, some way of extracting out some of the things that you are interested in the actual eye tracking data files. Now, what is contained inside those data files, I want to show you, because that will then also let you then see just how much easier it is to actually see the data in these files. So to do that, you can't actually look at the raw files, but there is this little program which lets you convert an iLink data file. So this EDF is the iLink data file, and it converts it into a text file that then I can actually open up in anything. So I'm just going to open up this come on. Okay, I'm going to cheat. I'm actually just going to go. So inside the data viewer, there's some sample data for you to actually look at. So in this case here, you see I've got picture, text, and dynamics. So I'm just going to take this picture one. I'm just going to drag this into the menu here, and then I'm going to convert this into an ASCII file. So you see here, and I can do this with multiple files. I just dragged it into, so you can either select it if it works, or you just drag and drop onto that, and what it'll do is it'll convert the iLink data file into what's called an ASCII file. And this you can open up in any text editor. So on my Mac, I've got a text edit. There we go. So this is actually the raw eye tracking file. All that data which is collected, this is actually what's inside that file. So the first part is what we call the header information. So this basically tells us some of the basics of what is actually recorded. So in this case here, It has the date of the experiment, which is 2002. This is quite an old file now. What type of data was recorded? So in this case, it's a file included binary information, event, sample information, and anything tagged. It was recorded on an iLink 2. And it was recorded within Experiment Builder 2.0, a long time ago. So the header just gives us some basic information. It tells us about the type of eye tracker that was using. Next up, it tells us about, well, what was the screen size, what was the refresh rate of the screen, and then it gives us information about the calibration information down here. So if you remember when I was talking about recording the calibration information as you went along manually, this is because you can eventually find it. So say for example, this is all the raw calibration information, and down here now we've got our, if you look here, the calibration was good, the validation was good, the average accuracy was 0.17 with a maximum error of 0.36. So in this case here, this is a good calibration. So in this case, it's quite easy for me to find that information, but I'd have to go through and manually find this. If you have a case where you've got bad calibration, then you would have to scroll down every single time. You see, this is a data file, very big, and so if there was a recalibration at any point, then I'd have to kind of look down and find that information, and it's kind of clumsy and annoying, and you'd have to do this for every single file. So yes, you can find that information after the fact, but it is time consuming. It's much easier if you just record that as you're going along. So it has a calibration, it has a validation, and then what you see here is you've got a series of numbers. This first column of data is actually the timestamp. So this is the computer, as soon as you start turning it on, starts to increment. And in this case here, it's actually incrementing by 2 milliseconds because the iLink 2, this was recorded at 500 hertz. 500 hertz means you're recording one sample every 2 milliseconds. And so what it's giving you is it's giving you the timestamp. It's the first column. When was the sample taken? It then gives you the gaze in terms of both X and Y position on the screen. So in this case here, you can see the first samples correspond to roughly about the middle of the screen. So without seeing the experiment, I could guess that this person started their experiment by probably having some sort of fixation marker in the center, getting people to look there. Yeah.
How do you, in the first column, how do you interpret that figure as the time?
That's just that's what it is.
But I mean, should we?
It's in time in milliseconds since you turn it on. So what you can then do is have that relative to this. So you can say, for example, have every other time. So it's just incrementing by 2 milliseconds at a time. But that's just how the eye tracker records the data. It doesn't record it in hours, minutes, and days. It records it in terms of clock cycles since the computer was turned on. Yes. Oh, no. Okay. So then you've got the next column is your X data, then you've got your Y data, and then finally you've got your pupil area size.
Is there any way you can tell the program to standardize the timestamp? Like, let's say I want to look at people's fixations over time, and like the trial is like 2 seconds.
You can, not in this, you can in Dataviewer. And we'll show you how to do that today. But in this, you would have to actually go back and do some math. And so what you would do is look for the smallest timestamp. And then say if you're doing this in MATLAB, say for example, I would create a column of time, and I would say the new times equal the old times minus that original timestamp, that very first timestamp. And then you would have something incrementing up from 1, 3, 5, 7, so you every 2 milliseconds. It is possible, and if you want to do some custom analysis, which is not available in Dataviewer, you could still do this in MATLAB. It is much more difficult to do, and that's for a whole other course. But it is doable. So really, that's, and as you can see, here we've got I mean, we've got a lot of data. And this is just one subject. In fact, in this here, there's about 5 million lines of samples from one subject. So anyway, that's what's inside the data file. So, and you always have that information. And that information, once a data file is recorded, we cannot touch it. We cannot edit it. So whatever you do, that will not save as an EDF file. So once that data file is created and produced by the eye tracker, that's it. It's fact. You cannot edit it. You cannot go in there. And anything you do will not be saved. Okay? So this is kind of fun if you want to go and do your own analysis. If, however, you're amongst the majority, you don't want to do that. You want to have the analysis kind of done for you. And for this is where we're going to use our Dataviewer. So hopefully by now you've all installed the Dataviewer. Dataviewer by default, so right now we're at Dataviewer 2.6. It works on Mac, PC, and Linux. In demo mode, it'll actually let you run. This is unlimited, but it runs with limited functionality. So what it'll do is only let you analyze 3 separate files, and only up to 5 trials per experiment, and only 50 events per trial. But for the purposes right now of showing you how it works, this is plenty. So when you open up Dataviewer, you get the nice, this is what it looks like. So again, it looks very similar to the experiment builder setup. On the left here, you have the sort of the panel which lets you inspect different parts of the data. So in this case right now, this is an untitled EVS, so iLink viewer samples. So EDF is iLink data file, EVS is an iLink viewer of samples. So let's just open up an example. So again, to do this, you can actually import data in different ways. So in this, I can either import a single trial at a time, or I can actually import multiple trials. So say, for example, you run your experiment and you've got 100 subjects. Most people are still unaware that you can actually analyze the data all in one viewer file. So people still will create one viewer session per subject per experiment, and then try and collapse it afterwards. Dataviewer really lets you get around that and lets you actually manipulate the data in different ways across multiple subjects. So as long as all subjects have run the same experiment, you can actually analyze them in the same data view file. So it's kind of useful that way. In this case here, we're just going to import a single iLink data file.
When you say same experiment, does that take into account that you may have one or two or three experimental groups and a control groups?
No, you can import all that into the same, as long as you have a variable, and we'll show you in a minute how you use that. You can actually rearrange the subjects based on any variable that you have. So if you've got a variable in your, so say for example you're running with condition 1, condition 2, and condition 3 across groups, you can import them all and then sort out via those conditions and actually analyze and create data results per condition in Dataviewer. I mean, this is really the great thing. It's a great way of, as long as you've got the experiment set up right and you have those markers and those variables, which you all learned how to do last time when we were doing experiment builder. So when we were saying results, did they get the trial right or wrong, you can actually import all the data and then resort out the data in terms of analyzing trials which are right versus wrong separately. It could be condition 1, condition 2, patient population versus control. It doesn't matter. As long as those variables are somewhere in there, you can then reorganize afterwards in Dataviewer. So if you go into open up the iLink data file, again, I'm just going to go to the iLink data viewer, go to the samples, and I'm just going to load up the picture example for now. this is what happens. So right now, you can see we've got on the left-hand side now in my inspector, you see my experiment. I've just imported a data file called picture. There are 3 trials worth of data in picture. Trial 1, trial 2, and trial 3. Okay? What you can also see on the right here is one of the different ways in which we can view our data. So when you import it, the import works by a number of different. You can actually set up a preference file for what you actually want to import. In this case, we're importing all the data, and you see, so it took a few seconds to load up, and that's because if I go into my preference setting here, and I click data loading, there we go. Why is it not letting me? Well, I should be able to click here, but I don't know why. So if I click on the data loading, it would give me options for what I actually want to import. So I can choose to import everything, or say for example, I don't care about the sample data, I only care about fixations and saccades. There's an options then I can toggle off loading up the sample information and only load the fixations and saccade. When you do that, the data files that this results files tend to be much smaller, because instead of having 1,000 samples per second, now it only has fixations and saccades, which are between like 3 and 5 per second. So the files are faster to load. The data, the actual results files are much smaller, and everything will go much faster. But now I actually want to keep the information about. I want this. I want the sample information because we're going to use that and show you how you can use that later on. There are other preferences as well, which we'll talk about as we're going through today. So once you've actually loaded up the data, the very first thing you want to do is actually to save it. What's nice then is that now you've loaded up all your, in this case we've got one iLink data file, but if we say, saved, I don't know, 100 different experimental participants, we've loaded them up, that will take you quite a while, especially if you're loading up sample data. If you want to do that, set it loading, go have a cup of coffee, go grab a bite to lunch. It'll take you between, depending on how long each trial is, how many trials you have in total, and how many participants, it could take you anywhere between 1 or 2 minutes and 1 or 2 hours. But the nice thing is you only have to do that once. Because once the data is loaded up into this, you can then save this as an iLink results file. So again, here I'm going to click Save As. I'm actually going to save my iLink viewing session, so this EVS, into the same folder as where the actual results are kept. And this is a good rule of thumb. So this way you always have your data and your experiments and all the analysis all in one single folder. So it's a good rule of thumb just to keep saving the data into the same folder. So it doesn't have to be the subject folder, but at least where your experiment, your EDF, your experimental set of files is, save it in that folder. So in this case here, I'm going to choose that, and I'm going to call this something useful like picture analysis. Again, this will just take a second. The larger the file, the longer it will take to save. But now it's saved. First of all, now I don't have to reload that data back in. It's always going to be contained inside this folder. So instead of having to go through that long process every single time you import data, you just do it once. That's it. From now on, I can now just open up this and analyze the data. Also, I can now edit the data. So say, for example, in this case here, I've got two trials, which are the same. So here I've got kind of an intact image. Here I have a blurred image. And here I have something that is completely different for whatever reason. Say, for example, I don't want to analyze that particular trial. I've got a screen I accidentally left in. I can actually remove that information just by right-clicking and remove from viewing session. It'll say, are you sure you want to do this? And I will say yes. And there we go, it removed. Now, that data is still in the original iLink data file. Remember, we cannot touch, once those are closed by the experiment setup, we can't edit those and touch those. So I can always go back and re-input that data again or reanalyze it in a different way. But for now, it doesn't look the same as the other trials, and so I'm just going to exclude it. And then I'm just going to click Save again just to make sure that's now saved in my experiment. So there we go. So now I've got my 2 trials worth of data here and here. By default, it'll come up with this trial view. So here we've got, this is the overall trial. So in this case here, we have this nice picture of a street. I think when we were doing the examples upstairs, all of you saw this experiment. And so by default, it'll only show you the fixation information. So you can see the fixations are drawn as blue circles on this view. So this is the trial view. It's kind of the sort of default, simple way of just looking at the eye movements of the entire trial. So the circle size is a kind of visual representation of how long they spent looking at a particular location. The actual number that's printed beside the circle tells you the number, the duration in milliseconds. So already you've got a kind of a very simple visual representation of what's going on. On the left-hand side in my inspector, I have actually the actual individual fixation. So this is the very first fixation. So if I click on it, you can see that my first fixation corresponds to the center of the screen. So you can see here that the fixation duration there was 464 milliseconds. So again, here I can look down here and I get the information about each of the fixations, and I can toggle through those. Also, I can select them on the screen. So in this case here, it'll tell me this, as I move around, it should, I don't know why this is not doing it, but it should tell me where the current fixation was. So in this case here, the fixation started there, ended there. What was the average position? Where was the next fixation? Where was the previous fixation? This is all information that's kept inside, and you can toggle through this information just by looking around here. I can also bring up other types of eye tracking. So in this case here, I can bring up my saccades. Saccades are displayed in yellow. And it's a yellow arrow with the arrow head indicating the direction of the saccade. So in this example here, you see the arrow is going from here down to here. And so you'll actually get, this is showing you the direction or the path of where the fixations are actually going. I can also mark blinks on the screen. I can also import the actual raw sample data. So the dark blue here represents the sample per sample of the eye tracker. Again, this is was recorded on an iLink 2 at 500 Hertz. So in this case here, each blue dot, and the dots are actually very small here, represents 2 millisecond sample. I can also put up messages. So these green boxes now indicate messages. And those are indicated by this paper icon here. And again, remember I said you can send messages to the eye tracker in your experiment to say stimulus on, stimulus off, whatever. You can actually have those embedded in the results file as well. So as you can see, there's a lot of information there, and it's a great way of kind of just visually looking at the information. At any point, if you want to save that, you can actually save that as a results file. It saves it as a TIFF file. Again, this is a really useful thing. That kind of visual representation is great when you're showing slides during a talk or a presentation of your results. Analyzing it's less useful, but if you want to show like a prototypical ideal participant result, this is a way of actually taking that data and outputting it to an image file, which then you can put into your manuscript, into talks or whatever. So if you remember back when we were talking about eye tracking at the very beginning of the course, I showed you examples from the Kaus-Handro and Henderson paper of someone doing free visual search versus searching for a particular target. Those maps were actually produced using this exact feature because they were recording on an iLink. So it's a great way of producing a figure to kind of show just visually what the participants were actually doing. The other way in which you can do that is to create a video. And so this here, the second way of looking at the data is what we call the animation playback mode. This is, in terms of analysis, it's not that useful unless you're doing video-based stimuli. Obviously, if you're doing video-based experiments, and we're going to deal with that next week, but if you're doing video-type experiments, this is a great way of kind of looking to see how the person's interacting with the stimulus, or persons. Because what's nice as well is here we've only got one participant worth of data. If I loaded in multiple participants, it'll actually overlay either an average eye movement or an individual scatter of the eye movements onto this display. So let's just play this back. Again, you've got a very simple video control at the bottom that lets you play, stop, pause, rewind, or fast forward or skip. So let's just play this back. So this is playing in real time at the same speed as which the individual interacted with the video. Very cool. It's a little bit fast. It's kind of hard because it's kind of jittering around. So if I want to slow that down, I actually can. So down here at the speed level, you can see this is at 100%. So it's at the same speed at which it was recorded. I can actually drop that down to 50% and then replay the video. So now it's at half speed. Now it becomes a little easier to then see how the person is exploring the actual image. So this is really, again, this is a really useful feature when you're doing talks because, when you're standing up there and explaining the pattern of behavior, rather than having to replay the video 2 or 3 or 4 times to show the pattern, you could slow down the video and then show, okay, he's spending, this individual is looking around at the center here, is looking now towards the traffic light. So you've got the time in to actually verbalize the pattern of eye movements that someone is making. In either case, if you want to run it at full speed or at a slower rate, you can save that video. So if you go up here, there's this little save icon with a little camcorder in. That actually then lets you save the trial. Again, you can choose what type of format that you want. So on a Mac, you can save it as an MP4 or an MOV file. If you're doing this on a PC, it lets you save it as an AVI file by default. And then you can have it, you can have it compressed in terms of the video or full resolution. And again, it's a great way of producing a prototypical trial video, which then you could use for talks, or even now for most journals now that you put supplementary information up, you could put up an example someone actually doing the actual trial. You know, the great thing about vision experiments, you know, compared to questionnaires or something else, we get to show what people are actually doing while they're doing an experiment with an eye tracker. So it's a great way of, if you want to get your audience hooked, show them what, you know, you can say, okay, we did this, we did this, and we did this. This is what a trial actually looked like and how someone behaved in a trial. So it's a really useful feature for getting your audience interested. Like I said, in terms of analysis, it's not really that useful, except when you're doing video. So when you're doing video, this can be useful because there it becomes harder to actually analyze the data with the sort of traditional measures. And again, we'll talk more about that next week when we talk about video analysis. So that's this trial back mode. The last way of visualizing your information is what we call the temporal mode. And this is actually old school. This is probably the sort of how most, you know, those are so slightly older, this is how we actually learn to analyze eye tracking data. It's through displays that look like this. So what I can do here, I'm going to actually just toggle. I want to remove. Okay, so what we have here is actually the raw position of the eye. The red reflects the upward and downward, and the green reflects the left and right movement of, right now I've only got toggled the right eye. So, in this case, red is left and right. So this going up actually reflects left motion. This going down reflects right motion. Green, upward is upward, the eye going up in Y position, and down is it going down in Y position. So everything here, so X and Y movement in pixels are plotted on the same axis here. On this axis over here, what we have is the time. So this is how, before beautiful things like Dataviewer, this is how you used to have to analyze eye tracking data, by looking at these lines and interpreting them as being, oh look, this is an eye movement that is going upward and is going slightly leftward. So thank you, Dataviewer, for making our life much simpler. But it still is. It's still, for many people, is still a great way of actually looking at data, because again, this is, you're looking at the raw, what the eyes are actually doing. There's other information you can have here as well. So for example, if I click on this icon here, this eye-looking icon, I get a blue line which reflects the pupil area size. So if you want to do pupillometry, you've now got this sort of pupillometry data which is there inside the data file. And again, I can do this for the right eye. In this case, I've only got the right eye. If I have binocular information recorded, so if I also have the left eye, I could put that up as well. If there was a target on the screen, so in some of the cases where you have, if you had someone following a target, you could actually plot the target position and then look at things like how well the participant tracks the target. So you could have the targets change in space, in X and Y, and the eye movements, and then you could superimpose them and see, well, how good was the tracking ability of your participant? Was it lagging behind, which it usually does? Was it smooth pursuit, or was there occasionally a rapid saccade and change in position of the eye? So again, I know that here we've got some sort of pause in eye movements where we've got not much eye movement occurring. So I know that a pause in eye movements tends to be a fixation. Here I've got a rapid relocation of the eye from one point of the screen to another. that to me tells me that there's a saccade going on there. Again, I can toggle those on with the exact same as before. So here I'm going to toggle on the fixation, and so you can see now I have these sort of dark bars. This is where the eye tracking analysis algorithm has identified that the eye did not move for a period of time, and so it's marking that as a fixation. Here's another fixation. Here's another fixation. Again, you can toggle those and scroll through those, and in the inspector behind, it will also toggle those as well and give you that information. I can put up the saccades. Again, saccades are marked as sort of orangey yellow, and so you can see here these lines here are marked where we've got this rapid relocation of the eye. That's marked as a saccade. So it's a good way of kind of going through and checking out how good the analysis is capturing the actual eye. So if you don't trust the eye tracking analysis package, and hopefully by now you guys have a healthy cynicism that you should not trust the analysis package until you've seen it working. This case here, this is a way in which you can see, oh look, I've got a relocation of the eye. I would call that a saccade. Is my algorithm calling it a saccade? In this case, yes. If, however, it was being missed, well, why is it being missed? Why is that not being called a saccade? In this case here, remember, we're in the demo mode, so it's only going to parse the first couple of events, and then it stops the analysis. Okay, so again, this just gives you a very simple and easy way of visualizing different aspects of your data. This view is less used these days because now with the sort of spatial overlay models, this is useful if you're doing something like movement tracking for things like smooth pursuits, but it's been kind of superseded by the other types of analysis. But it still has its place. Like I said, it's a great way of checking to make sure the algorithm is effectively capturing the events that you want it to collect. So things like saccades versus fixations. Any questions so far? Okay. There are other things as well it can actually plot as well. So for example, it can plot things like velocity, acceleration, and again, these are tend to be sort of synchronized. So if I just take off the let's take off the fixation data, let's take off the messages. So you can see here the sort of acceleration and deceleration and velocity kind of occur at the same time as a saccade. So again, it's just another way of sort of verifying, if you've got a change in acceleration, a change in velocity, and you've got a sudden change in position on the screen, those three usually would indicate that you've got a saccade. If your algorithm is correctly identifying a saccade, that is a good thing. If it's not, that is a bad thing. So it's again, if you're looking at other types of analysis in other eye trackers, make sure you check to make sure the algorithms really are working and doing exactly what you want them to. Okay, so now we've seen the three different ways in which we can actually sort of view the data. I'm just going to go back and look at this back in that spatial mode because I kind of like this. It's kind of, again, this is sort of the most standard way of analyzing eye tracking data now, is just to kind of produce a sort of overall trial result. Now, like I said, one of the great things about Dataviewer is that you can rearrange the analysis in different ways. So for example, I can, if I've imported different participants, instead of having one picture file here, I'll actually have, participant 1, participant 2, participant 3, participant 4, and inside each of those EDF files will be how they viewed the individual data. say I don't want to do that. Say I want to sort of say I want to put up one image like this, but I want to have all participants' eye movements superimposed on that one image. So across all participants, or one group of participants versus another, I want to look at how that group that I'm interested in viewed that image. Well, to do that, you have to rearrange the data. And to do this, this is where those variables which you put in during an experiment, this is where they become very useful. And you can always go back and view those variables by going to this thing here. So you've got trial variable manager. So if you go into analysis, there's something called trial variable manager. If you click this, in this case here, it tells me, in this example, I've only got one variable. It's called type. If I want to go back and add more variables, I can do that as well. So if I go into the analysis, I go into the trial variable editor, you see now, okay, so this is the three variables that I was recording. So first of all, what was the name of the file? So the results file. So this is normally named after your participant. Then you have the trial number, 1, 2, 3, 4, whatever. Again, if you have that randomized, that trial number and the type won't correspond across participants. All the trial number does, it tells you what was the very first trial that they saw, the second trial, the third trial. So if you've randomized your settings, so when you, in your data source and experiment builder, if you'd clicked runtime randomization, those are going to be different on a participant-to-participant level. But in this case here, I've got the type of trial that they did. In this case, did they view a normal image versus the blurred image? I can always add additional columns to this as well. So after the fact, if I decide I want to add in new variables, so say for example, I forgot to say if the participant was male or female. I didn't record that in the file, but somewhere I've got a track of that information. I can add in more variables after the fact. So you could have male, female, age, any of these. So all that questionnaire data that you sometimes collect, you could actually, or after the fact, go back into the results file and manually edit them, or either you or the undergraduate slaves that you have in your lab can do this, where you can enter in that information here so that you could then rearrange the data amongst different ways. So, like I said, once you have that, and again, you can just go into the editor there and add those in. I can then go to trial grouping. And so in this case here, I'm going to rearrange my trials to go, why is this not? Oh, there we go. Type, and I'm going to regroup. And so now you see, instead of having it arranged by participant, now, if you can imagine, here would be all the eye movements for blurred, here would be all the eye movements for normal. Again, if I have multiple subjects, all the eye movements across subjects would be overlaid into the same image.
Could be, the more, of course, the more subjects you have, the more lines you're going to end up.
Yeah.
So it could be like.
And the other nice thing about this as well, that grouping can occur by different factors. So in this case here, I've only got one factor. I could group by, say for example, type of stimulus, and then whether they got it right or wrong. Or type of stimulus versus gender. Type of stimulus versus experimental group 1 versus my clinical group. Whatever you can either rearrange this by a single factor or by multiple factors. The more factors you have, the more summary images it will produce. And again, each of those is just for that particular set of conditions. So say, for example, if I had type of image by gender, I would have all the data in that one part of my results file, which had only men looking at the normal image, only women looking at the normal image, only men looking at the blurred image, only women looking at the blurred image. So if you think about, the different types of way in which you could parse your data, Dataviewer does it for you. You just have to think, oh, how do I want to reanalyze my data? And this is the great thing with the editor after the fact. So say, I know some of you are sex researchers, say you have a variable that is sexual orientation, where you have 0 being exclusively heterosexual and 7 being exclusively homosexual. You could then take that and reparse your data across those different variables for each image. Or you had a group of schizophrenics versus controls. You want to see how they view faces. Well, if you had face stimuli, you could have it separated by emotion, angry, neutral, happy, and then by controls versus schizophrenics. Again, this is one of the great strengths of this analysis package, is it really lets you rearrange the data relatively simply. It's just a matter of a click, and then away it goes.
Just to be clear, if let's say you have 50 participants,
Mm-hmm.
will it give me 50 overlays?
Yes, it will give you 50
or
overlays.
Or the means of the...
No, 50 overlays. Okay? Once you have that, so in this case here, I've only got one subject. Again, all the data would be overlaid, and then you can do some ways of regrouping your data or re-representing your data. So you can regroup them in different ways. The maps would change. If you wanted then to actually see beyond this, remember the other way in which we could show where people are looking is to do things like heat maps analysis. Well, if I save this up here, I save the image. If I use this, I can generate a heat map. So again, by default, it's going to ask me, well, where do I want, it's going to save this as an image. It'll save it as a TIFF file. So I'm okay with that as default. It's creating my heat map. Voila. There's my heat map. Again, I can toggle off the rest of the eye movement data. On the right here, it's giving me the actual axis of the heat map, going from 0 to the longest duration, which is summed across fixations as being about 1.5 seconds. So not surprisingly, you see, they start off by looking at the very center of the image. So that's the kind of the hottest part. But again, it's another way of representing the data beyond the individual. You could say collapse across individuals and across different eye movements in a particular area to see what's the general trend of where they're looking at in the image. Yes?
Can you change that scale?
Yes, in the preferences. So in the preference settings, there is an option in here, and it's not showing it, for, if you click there's an option for what you want to plot. So you could change from fixation duration to the number of fixations instead. So there are different ways of choosing how you want to output this in the type of heat map you want. And again, you see at the top here it says eye length fixation map duration based over the full interest period and full time period. And it gives you the the trial data for which participant, which trial, and again gives you the maximum fixation duration in milliseconds.
For each color level, there's a certain sensitivity.
Yes, and those are set in that preferences file. And for, I don't know why. Here we go. If I click there, there we go. So you see here, this is a setting. So here, this is by default, this is duration. I can change it to count. The other two, which are really interesting, so count density and count density duration. So it normalizes it. And so this is raw per second. You can normalize it per trial to be whatever the maximum was for that particular trial. again, here, sigma just tells us what it actually does here is it takes each fixation position and has a Gaussian blob that just kind of is thrown down on the page and adds those together. So in this case here, the sigma, the sort of the size of that blob, is set to be 1 degree. 1 degree because that's about the size of the area of the fovea on our retina. So if you're looking there, you would assume that you're foveating that particular part of the image, and so 1 degree is what most eye trackers use as default. In this case here, anything below 10% of activity. So if you only look at a point once during a trial, it kind of just discounts that. So that's why all this information over here is kind of excluded. Again, here you can set the colors for positive, negative, and neutral, medium activity. You can change the transparency. So in this case, it's 50%, so you can see the underlying image. There may be a case where you want to remove that and really just have it full color. You can do that as well. All of these are sort of variables that you can change quite easily. And again, once you finish that, you can save the image. So if you, again, it's saved by default, but you can go and actually, if you make edits to it or whatever, you can always go back and save that image. And again, very useful thing to have in talks or papers as showing sort of your prototypical trial result, or just to visualize the statistics of the eye movements. Like all of this we're going to analyze, and I'm going to show you how to analyze in a bit with numbers and statistics. That's not a problem. But sometimes it's just nice to show pretty pictures that kind of represent how people were interacting with the image. This is just one participant, yeah. So in reality, you can load multiple participants in. But again, you would do that just by saying file. You can import one at a time, or you could import multiple. So if you've run your experiment on the same experiment builder program, you'll have a results folder, and in there you'll have a separate folder per participant. You don't have to go through and click on every single file. All you do is you actually just click at the results folder and hit import. What Dataviewer then will do is it'll import every single results file in every subsequent subfolder. Again, very quick, very easy way of getting your data into Dataviewer. As soon as you've done that, though, make sure you save it. Okay? Because that way, from then on, you're analyzing your data and you don't have to re-import them every single time. Okay? What's also great as well is when you do this, when you import the data, it's always going to be imported with the same settings. So if you go to those preference settings, so here, now I know how to do this, you can see every file is being imported in terms of samples, fixation, saccades, blinks, all that information. Again, if I take off the samples, any file I then upload will have all the information except samples. Again, here by default, it's just in the general settings, it's going to say, okay, if both eyes are there, use the right eye for analysis. That's by default. You can toggle that off and then choose either to import the binocular information, and then you can actually in your event information, you can analyze by left or right eye separately, or you can, and that way you can say, okay, I'm going to delete one eye or the other eye. Again, this is where it just says, okay, well, where are my files? What's the display of the screen? The data filters is the other really useful thing. So this is lets you sort of change some of the information which you import. So for example, display blink saccades, yes or no. You can merge nearby fixations. So if your fixations are within, say for example, 1 degree, you could say, well, and again, depending on the analysis, you may want to say, well, if it's within 1 degree, they're all looking at the same object. Therefore, I'm going to merge those two independent fixations and call it one big fixation on that object. Again, rather than having to do this go through the data analysis file and do this by hand, you could just click that button. In this case here, I'm saying the fixation merging amplitude threshold is 1 degree. Anything within 1 degree of another fixation is just averaged together to call it one big fixation. So if I had one fixation that looked at one of your eyes versus another fixation that looked at the other eye, both of which were 500 milliseconds, I don't care about where you were looking at the face. I just care that you were looking at the face in general. I can merge those two together and just call it one fixation duration at the face of 1000 milliseconds. Instead of doing this by hand, the input, when you import the data, it would allow you to do this for you. Again, you can merge based on fixation duration. So for example, you could say, if any fixations were less than 150 milliseconds, they were just kind of glances. I don't care about those. I could set that to be 150, and it would not mark any fixations which were below 150 milliseconds. Saccade amplitude, again, if I don't care about small saccades, all I care about is saccade longer than 5 degrees, I could mark it as 5 degrees, and it changes the algorithm of how it defines a fixation, or a saccade in this case.
So when you're measuring an image or a line of text in terms of degree, how can you visualize where 1 degree is? How do you measure that on the image? So if you have a picture of face, how do you determine the degrees? How far apart the eyes are?
You have to analyze that in the data, and we'll get to the data analysis in a bit, but there's a way of analyzing it in the data results file when we analyze. So we haven't even started talking about the analysis part yet. We're going to get to that. The important one here is these two down here. So like I said, when you have a fixation that suddenly appears, you have a fixation point, and then the trial appears. That will actually, the person's eye is going to start usually at the center of the screen. If I want to include that information before, I actually have to toggle that off. Otherwise, what will happen is that duration will be trimmed to when the first stimulus appeared. So you're going to have that first fixation is going to be partially due to the fixation point, and then partially due to when the stimulus comes on the screen. If that is untoggled, that first fixation duration starts whenever it started looking at the fixation cross. Okay? What iLink actually lets you do is it actually lets you trim that so that first fixation duration is trimmed to the onset of the stimulus and not the onset of the fixation cross. So if you want to look at things like latencies, with how long do they spend fixating before they make their first eye movement, that's a really useful thing to remember, is that by default now, and this has changed fairly recently, by default, it'll actually trim that first fixation based on the onset of the stimulus. Now, in some cases as well, some researchers argue that you should actually discount that first fixation duration altogether because it is somewhat influenced by the fixation cross. And so there's actually an option here to hide that as well. So what will happen is in any of your subsequent analysis, that first fixation duration is actually removed. So if you want to look at things like average fixation duration across the trial, most trials you would tend to have a very long first fixation duration and then smaller ones later on, which would lead to a change in your fixation duration distribution, or mean. If you remove that, now you have a much more representative real fixation duration on average across your trial. There are some people prefer doing it one way, some people do it another. As long as you justify that you said, well, we're including any fixations which are from the onset of the stimulus and spanning fixations, which are what, if you're looking at a fixation where you looked across into the start of the actual stimulus, that's what we call a spanning event. Those are either discarded or trimmed. As long as you're explicit and you state how you deal with them, you're fine. There's arguments for and against. No one's going to shoot you down in a review for doing one versus the other, so long as you just say how you deal with that very first fixation. Again, most eye tracking studies do not do this at the moment. But you guys are going to be better. You guys are going to do it the right way. So those are all the sort of the import functions. We're going to take a breather here, and when we come back, okay, so far we've been dealing with the entire data file. Now, sometimes you don't want to analyze an entire data file for different reasons. Sometimes you don't care about the entire duration of the experiment, or you care about a particular period of time, or when a certain event occurs, or you only care about when people look at certain parts of an image. And so for the rest of today, I want to talk about how you can separate that data file into either different time periods or using different interest areas to see, what happens when are people, instead of looking at the entire image, you only care about when they look at a particular part of an image. And so to do that, we do what's called an interest area analysis. And then finally, I'll show you how to analyze the data. That's the easy part. That takes 5 minutes. So right now, we're seeing the entire trial's worth of data. And I know that because up here, this is actually what is termed the interest period selector. So you see here right now, it says full trial period. That is, the entire duration of my trial is currently being presented. Now, say I don't want to do that. Say I only care about a certain period of time or between certain messages. I can actually then selectively choose to only show and analyze particular periods of time or when a certain event is occurring on the screen. So to do that, I select my full trial period and I click Edit. This brings up the Interest Period Manager. So as you can see right now, there is nothing in there. You can actually import interest periods from other experiments you've run. Say you've got 3 experiments which are interested in a particular factor. You can actually transfer those between. You can export interest periods, or you can create new ones. So this up here is a new one. So you see here, new interest period. I click that. It brings up the settings. And so here you've got, this could be based off of a message. It could be based off of an event or a time period. So for example, I'm interested in looking at a particular time period or button press or duration. I could say, okay, I'm interested in looking at first 1000 milliseconds. Obviously, by default, it's calling it a very imaginatively named new interest period 01. Please change that to be something that is meaningful. So first 1000 milliseconds tends to be a really interesting. Say how you're selecting it. If this were done by messages, again, I could put what the message is in here. So for example, stimulus on, or decision time, or whatever. If you have a marker that is marking a particular event that's occurring, and that's really what you don't care about the rest of the eye movements. or you care about the eye movements related to that event, this is a way of only selecting those eye movements. Now, one of the other nice things as well you can do here is you can actually offset the start of that event. So say for example, and this is really going to be useful when we talk about pupillometry. Say for example, I am only interested in the first 1 second after the onset of a stimulus in terms of the pupil response. Well, in order to actually do pupillometry, we're going to talk more about this next week, and I'm going to show you how to do pupillometry. We need to also know what's the base resting level of your pupil size. So what you could do here is say, okay, I'm going to collect a period of time before the onset of the image, and then the 1 second afterwards. So then you've got baseline pupil, and then the onset of the image, whoa, pupil size change. This is usually related to the fixation point, yeah. But whatever it is, it'll record, so from that message or from that time point, you can record a period of time before it. So if you want to look at how eye movements were before and after an event, this is a great way of actually then recording that and only analyzing the information related to that event instead of the entire trial. And again, this could be message-based, this could be based off of a button press or a keyboard press. So if you want to look at eye movements before and after they press the button making a decision, you can do that as well. Okay, and then somewhere up here, it's supposed to have my, there we go. So if I want to have, so you see here, this is the, it's not letting me do this because it's in demo mode. Here's the full period. Here's my sort of selected period. So it's a way of sort of trimming and looking at different types of eye movement. Instead of having the whole time, you can select messages. So, you know, in this case here, we've got no message. Do we have a message? Oh, there we go. We've got a message here that said, I want to know what this message was here. Here. Where screen capturing never works. So whatever the message is here, I could synchronize around that event as well. So there are different ways in which I could sort of trim that down. Again, that allows me to sort of, again, instead of analyzing all eye movements, only around a particular period of time. The other thing which we're particularly interested in is, of course, interest areas. So, you know, if I want to say, well, I could draw an interest area around the car if I was interested in seeing how people view cars. I could do it around the traffic light. I could do it around the building over here. Well, if I want to sort of look at the eye movements in those areas, I can do that by just selecting those eye movements in general. So say, for example, over here, I can highlight those, and in my variable window you see over here, it now highlights the eye movements related to inside that particular box, which I've selected. So that's a quick way of doing an interest area. But if we want to do something that we can then analyze later, this, you know, obviously as soon as I click away, you know, it changes my interest area as I click away. Say I want to now actually have a more permanent representation of that interest area on the screen. Well, to do that, I can actually draw interest areas into my results file. And I can do that with these three buttons up here. So this draws a square interest area. This draws a ellipse interest area. And finally, this other one over here does a free form. So I can take this and I can say, for example, I am interested in looking at how often they look at the church spire over here. I can sit here, I can draw my interest area around the church spire and really kind of focus it in exactly on where the church spire is. And then if I hit enter, it'll ask me to label it, and I'm going to call it there we go. And so now I have my interest area. So with freeform, if you want to close up the freeform, you have to hit enter. Otherwise, it will keep on adding as you're going around. Yes?
Would you recommend drawing interest areas like before you run the experiment or after, or like what's the difference?
You can do both. In Experiment Builder, you can actually draw interest areas around your stimuli from the start. Or you can go in afterwards. It's purely up to you. In some ways, it's better to do it before you start running experiments, but at the same time, if you forget it, or you suddenly want to redefine an interest area, you can always go back and do that in Experiment Builder afterwards. So in each of these trials, there are these, you have these interest area templates. There. So there's custom interest areas. So if you have predefined your interest areas, this will already have an interest area set already in there. You can always go back and delete that or add to it or modify it afterwards. So it's really up to you whether you want to do the work before or after. Again, if you're averaging over here, I can take that interest area and I can actually copy and paste it between different versions of the experiment. So I can take it from here. Ooh. No, I don't want that. There we go. I can instead, I could go back here. I can select that interest area, and I can actually right-click, and it gives me an option to copy and paste it into different screens. So it's purely up to you.
Can I copy it into all the other
Yes.
participants?
Yeah. So in this case here, because this is a range with all participants added in, I only have to do it on the top image, and it would actually automatically apply it across all the images underneath, all the participant views underneath. So if I draw this interest area, instead of having it on the trial, if I have it highlighted on the normal, which is what I had before, this, yeah, every participant's data underneath would have the exact same interest area in their results file now. Now, when it comes to defining interest, so never, ever, ever do this. Never go exactly on what you're interested in, because eye trackers are variable in their sample quality. Every participant who you run, they're never going to have the same level of accuracy. Yes, we're calibrating them. We're calibrating them to that specification which we talked about upstairs. So you want to have the average error to be less than 0.5 and the maximum error be less than 1 to be a good eye tracking study. Obviously, if you're more stringent there, the better the quality of the calibration, the better the quality of the eye movements. But they're going to be varied anyway. As such, here, I've got these eye movements here, which are probably related to looking at the spire, but they're not exactly on there. Right now, they're being excluded from my spire interest area, so it's only going to count those eye movements which are related to inside that interest area. So there's no defined rule at the moment in terms of how big or how much area around an interest area you should have. As a rough rule to keep in mind, though, you want to keep in mind about what's your average error rate. So your average, you said, I'm saying we're going to calibrate with an accuracy of at least half a degree. What that means is your interest area should be half a degree bigger than the actual object itself. if you want to really then capture the eye movements, because even within the individual error, they're still going to count towards that interest area. Half a degree on our eye tracking system actually corresponds to 15 pixels. So if I do something simple, let me put down a simple rectangle down here. Let's say my car. And I'm going to call this interest area car. Okay, this is way too tight around the car. I can actually then set this. So for example, here I can add, in this case here I'd have to subtract 15 pixels, but I can take away 15 pixels from each, or add 15 pixels to the left, to the right, to the top, and the bottom to expand that area so that it encompasses not only the object but also the amount of error in my eye tracking around that object. That's how you should be doing interest areas. If you can do that, you're going to get much more realistic representation of where people are actually looking at on the screen. Okay? So, online, there is a document by Lisa Oakes. It's in the papers folder, and it's how to run an eye tracking study. This at the moment is the only place where they actually give a recommendation about interest areas. So what they actually recommend in there is, first of all, you should define your interest areas. Also, not just say, oh, we put an interest area around the object. Report somewhere in an appendix or supplementary data online what the coordinates of that interest area were. How big was it and where was it located on your screen? So you can see here, if I click on that interest area, it gives me, this is a rectangle. It tells me the left position, the top, the right, the bottom, and the center of where that interest area is. And it also tells me the area in total of pixels encompassed by that interest area. Somewhere in your results or supplementary materials, you should be reporting that, because if someone wants to come along and replicate your experiment, you don't do that, they cannot replicate your experiment. They'll be drawing their own interest area, which may have a completely different set of properties, which then change, again, up here, if my interest area only encompasses the spire, I'm going to have a different set of, if I look at the number of fixations inside that interest area, it's going to be different than if, say, for example, I had a 15 degree pixel edge that was around the object. So make sure you're explicit in reporting where those interest areas are located and the properties, where they're located, the size of those. Because that's going to change the results, and it could change the results completely depending on how those are set up. Again, right now these are all the same color. I can do some things like, again, I can do some very simple ways of, if I'm not in screen capture, I could click on there and actually just change the color of that interest area quite easily. Again, much like before, it would bring up a little color window, and I could change the color to be green or have it some sort of color-coded, making it easier for me to find. Again, if I want to copy that interest area, I can just right-click on it, click copy. I can go over here, I can click paste, and I can paste it down and actually then move it around to somewhere else. That's really good if you want to have, say for example, you want to say, are people looking at the left object versus the right object? Or in your experiments where you were looking at left and right animal, you could create an interest area around one box and then copy and paste the same size of interest area on the other box, and then report that the interest areas had the same height and width and area, but were centered around here and here. Again, if you do that, you're better than just about every eye tracking study that's out there. And I can do this for different objects. I can do, and I can toggle these on and off at any point. So up here, this little icon here lets me toggle on and off the interest areas. And like before, if I save my results, it would save the results with those interest areas or without, depending on if it's toggled on or off. So you'll see in journals, interest area analysis is quite popular as a way of sort of, eye tracking generates a lot of data, but sometimes you want to say, well, how often do they look at this image versus this image? Were there more fixations looking at this part than the other part? By using the interest area, when you run your analysis, you'll be able to actually break apart the eye movements in terms of each individual interest area. And so you will have things like what was the number of fixations in that interest area? What was the total fixation time or dwell time spent inside that interest area? And then what we'll see next week, this becomes critical when you actually try to start analyzing reading research, eye tracking studies. So today I've been keeping things very simple. I'm only doing pretty pictures. Next week, we're going to do the more complex, the three most complex type of eye tracking analysis you will do: text analysis, moving video, and pupillometry. They get a whole other talk about them. So, okay, but I've got my data, I've parsed it, I've selected a particular time period or a particular interest area, and I've done all of this. I've cleaned my data, I've looked at it, I've made it all pretty, I've got my prototypical videos, I've got my prototypical images, I've got my heat maps. Again, all of this is all very well and good, but sooner or later, you want hardcore numbers. That data you want to crunch. This is really, all of what I've been talking about so far for the first hour and a half has been the pretty stuff. Now we want to do what really you want is actually the raw numbers. And for this, we go to the analysis menu. So you see here, along with those trial variables, you have this reports. The eye tracker will, the Dataviewer will give you a number of different ways in which you can analyze your data. Probably the one that's the one you should do first is generate what's called a trial report. This is really the most simplest type of way of extracting most of the statistics you're interested in an eye tracking experiment. What it will give you is one line of text per subject per trial. So if we go here, so now these are the variables you can select to analyze. And there are lots of them. Lots and lots and lots and lots and lots and lots. So some of these are going to be more important and less important depending on the type of experiment you're running and what you want. Obviously, things like so up here we should now, there we go. Now we have type. In this case here, I want to know my type here is the type of trial I had. So blurred versus unblurred. So the variables, things like what was the stimulus on the left and the right, the sound, whatever, those things, those variables which you enter in an experiment builder are available at the very bottom of the available variables. So those are obviously things you're probably going to need to have information about in order to analyze your data. Then there are other things. So for example, average fixation duration. So across the entire trial, what was the average fixation duration? What was the average saccade amplitude? Number of blinks. Experiment duration, you could have number of fixations in total over the entire trial. What was the maximum fixation duration? When did that occur? What was the minimum fixation duration? When did that occur? How many interest areas have you got on the screen? At what sequence did they look at the interest areas? How long did they spend looking? What was the interest period? So this up here, how long was it? Pupil size. So if you want to know the what over the entire trial, what was the average pupil size? You can get that. What was the maximum size and when did that occur? What was the minimum size and when did that occur? Those are very simple ways of doing basic pupillometry analysis. Again, we're going to deal with that next week, but that's all in there. Reaction time. Saccades, number of saccades, number of sample, there's a lot of choice in there. And so over here somewhere, if I select this, there we go. You see, and it actually gives you, or it should give you, a definition of what each of those actually represents. So if you click on those windows now, you'll see that. So for example, an average fixation duration is defined as the total number of fixations, blah, 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 in that area. If I hit next, it'll always do this. It'll always say before do you want to save the file? Yes, fine. I'll save it. I'm going to just save this on my desktop. And I'm going to call this trial report. For picture. And there we go. So if I now go down here, and if I open this up in Excel, so here we have trial index 1 and 2, normal, blurred, average fixation duration, all of these different variables which I have, those are output into an Excel file. But you see it's only one line per trial. So this is great if you want to go through and get quick information. Fixation duration, how long they spent, reaction time, all that sort of quick stuff. You can get that with the trial report fast and accurately. And you can get things like, maximum size of the pupil, minimum size of the pupil, and average size. So very quick, very easy way of extracting information on average. And it's a great way if you've got a lot of trials and a lot of subjects and you just want to get a quick idea of what the eye data look like. That's the way to do it. Now, if you want to go into more in-depth analysis, well, there are different reports for different types of eye movements. So for example, there is a fixation report. Again, the fixation report has some of the same things. So somewhere down here, it'll have trial type. It will also have information about fixation duration, fixation count. And what that'll actually do is on a fixation to fixation basis, it will tell you the first fixation, how long was it? Where was it? How big was the pupil size on that fixation? The second fixation, again, it would do the same. The third, it will do the same. So here, instead of having one line per trial per subject, you're now going to have multiple lines telling you information about how long the fixation was. You can select where the fixation was. How big was the pupil at that size when it was looking at that particular part of the image? It also gives you, it'll give you options for other, so not just the current fixation. You can also look at the previous fixation and the next fixation. So if you want to look at how, say for example, I'm interested in a startle effect. So when someone looks at a particular part of an image, I go, No! Okay? What happens, so what normally happens is we know from other eye tracking studies that fixation that they are currently on or the next fixation will be 3 to 4 times longer than the preceding or the subsequent fixation. Again, I can do that because I can look at the previous fixation, the current fixation, and the subsequent fixation. I can output that into the same analysis. So you would have a column for current, previous, post. So you're interested in looking at how fixations change as a function of what they're doing, or an event or a change on the screen, or someone screaming at them, then you can actually look at that quite easily with this type of analysis. And again, when you save the results file, it will save as a Excel file. And again, it has even more, because everything's in triplicate, because of current, next, and previous, it has even more variables you can actually look at. So, was there a blink during that fixation? What was it? What was the previous fixation direction? So, was it up or down, or was it before or after? Are people scanning their eyes in a particular pattern on the screen? Interest area. So, were the fixations in the interest area? So again, here you can actually compare fixation based on whether the fixation was inside an interest area or outside of the interest area. Lots of choices. And again, if you want to know what any of these actually are, all you can do is just click on it, and it'll actually define, in the variable definition, it should show up down here on your version. When you click there, it'll tell you what that particular metric is recording or reporting. So if you don't know which one to do, you can toggle through them and show and read exactly what each variable is going to give you. We can do this for saccades. So, current saccade amplitude, current angle, average velocity, direction, duration. Does it end in an interest area? So, did they actually land in an interest area? Did they start in an interest area? What was the peak velocity? What was the average velocity? Start time, end time. Which eye was used? So again, if you're having binocular information, you're selecting one eye, you can have that in the results file. And again, next and previous as well. And again, that'll give you things from that. You can say, again, it would say saccade count would give you saccade 1, here are all those metrics. Saccade 2, here are all those metrics. Saccade 3, here are all those metrics. So you're going to have multiple lines. The more saccades people have per trial, the more lines you will have per trial per subject. Results files get bigger. If you want to do an interest area report, so again, I want to look at things like, well, how long did they spend looking at the traffic lights compared to the car? Well, I can do that. So I can say, I can have the interest area label somewhere over here. I can select that. I can say I want to look at, well, what was the dwell time? So what was the total? And dwell time, it takes all the fixation times inside that area and sums them together. So dwell time is a really useful, if you want to say, how long do people look at this image versus the other image? This is used a lot in developmental. In fact, it's the main metric in developmental eye tracking. That's how you get it. You put an interest area around one, you put an interest area around another, and you look at total time.
Can you do, like, now you have one light, could you do many areas
Yeah.
and then bunch them together?
You can add them up together afterwards, yeah, in your analysis. Or you could actually draw an interest area that encompasses all of them. Yeah, so you could have individual. So I could say car, traffic light, pedestrian, and then I could have another interest area which encompasses the lot, that says street. And so you would have the individual interest area and the total. That's possible. So dwell time will give you in milliseconds how long they looked at a particular area. Sometimes, though, you may want to express that as a percentage of the total time looking at the image. People like using one or the other. So you see dwell time percentage. So if someone's viewing an image for 10 seconds and they spend 1 second looking at the car, okay, they can express that as 1 second as being the dwell time, or 10% of the total viewing time was spent there. This is really good if you want to standardize. So if you've got an experiment where instead of looking for a fixed period of time, you're letting people scroll through images at their own pace, dwell time is not the best metric there. Probably it's better to report it as a percentage of time out of the total time that they spent looking there. So if this were they looked at this image for 10 seconds, they spent 1 second looking there, my dwell time is 1 second, my percentage dwell time is 10%. If this were for 100 seconds, and they spent 10 seconds looking there, my dwell time now jumps to 10%, my percentage dwell time remains at 10%. Okay, so if you think about it, raw dwell time changes from 1 second to 10 seconds. Well, 10 seconds they're spending more time looking there, they must be more interested. Percentage dwell time, it's the same across both time periods. So you can interpret that as you will. But you've got the choice between the two. Again, what was the first fixation inside that area, and what was the first fixation duration? This is usually important because the first fixation tells us when that occurs and how long it is the initial look at an image or initial look at the object. And that's very related to how salient it is or its role in the current task. So it's worth reporting as well as the total dwell time, the total duration inside that area. And again, we'll talk more about that when we're dealing with reading metrics next week, because there's a very clear definition in reading between what's called first pass duration. So how long you look at it, the very first fixation, versus total fixation duration, or total dwell time. Again, where was it located? X and Y. Number of fixations actually inside of an interest area, again, is another useful metric to report. Usually fixation duration and the number of fixations will be highly correlated, so there's probably no need to report both, but sometimes people prefer count, sometimes people prefer duration. Again, where was the last interest area fixated? Where was the next one? So you've got the replication. Where was the second fixation inside the area? Where was the third fixation inside the area? Again, less interest here, more interesting next week when we deal with reading metrics. So again, you've got a whole bunch of variables that you can measure there. You can also look at the messages and see when they came in and when they had as well. And you can do a sample report as well. So this is on a sample-to-sample measure. Again, all of the metrics are in there. So eyes, pupil size. This is really, when we do with pupillometry, this is probably going to be the most important thing, because this is a way of actually getting that pupil size on a millisecond resolution, which is what we'll look at when we deal with pupillometry. But there's all sorts of other, where in the eye, where is the left and right eye position. So if you want to go and really look at data on a millisecond to millisecond, this will produce that data file, which will be huge. But you can do that in terms of where is X and Y, what's the acceleration velocity of the eye right now, what's the pupil size on the left and right eye, So all of that information, again, this allows you, especially if you want to do things like looking at tracking a target, you could produce where the X and Y position is and of a target, where the target is, and then you could have those and then plot those in Excel or MATLAB or whatever. It's another way of getting all that information out and then analyzing it later on or presenting it in a different way. You can also change the sampling resolution of your data file in the sample report. So at 1,000 hertz, you're going to have 1,000 lines per second. A lot of data. Even through pupillometry, that's way, way, way too much data. You can actually resample the data file to a lower recording level. So say, for example, here, I'm recording at 500 hertz. That's even at this level, it's an insane amount of data. I could resample that and sample it down to, I don't know, 125 hertz or something else. And if I do that, what it'll actually do is it'll go through and subsample that whole data file and only report it at a lower rate. So instead of having 500 lines per second, I'm now only going to have 125 lines per second in sample. So again, reduces the size of your analysis, makes it a little easier to deal with. Again, the data is not being changed. Remember, those EDF files which you started with are all still there. You can always go back and reanalyze them at the higher sample rate. More likely than not, you will not need that level of precision. Like 500 hertz, even 1,000 hertz is overkill for most types of eye tracking study. So you can go back and make those data files or the XBOT files much smaller and easier to handle. And again, you can look at, you can do some time course bidding analysis as well. This lets you, instead of looking at the entire thing, again, this is another way of kind of subsampling down. You can look at it over, instead of looking at it on the huge style, you can look at it every 20 milliseconds or every 100 milliseconds and look over that entire time period. What was the average fixation duration? What was the pupil size? And again, this is another way of kind of breaking down large data files into something that's more manageable. So for example, if you don't care about ultra precision in terms of pupil size, all I care about is what's the average pupil size per 100 milliseconds, I can bin that. I can say, okay, well, I'm going to make this 100 milliseconds. I'm going to analyze the first 2 seconds of the trial, or up to, it would actually be 2,000 times 100 bins. So say, for example, I only care about this for the first 2 seconds of a trial. Let's look at the first 20 bins. And I want to have pupil size. So somewhere over here, there we go, pupil size. If I do that, again, it's going to ask me to save it. I'm going to put it on the desktop. I'm going to do picture pupil. If I go on the desktop, there we go, picture pupil. If I'd selected it properly, here it would have, you see here it's got the, for trial, here's a picture. This would be for the first bins. This is for picture 1 for normal. This would be for the blurred. And it would have the picture label here. Or pupil label, pupil size. So again, it's just another way of breaking down your data into whatever you're interested in. You don't have to analyze everything. Some people do, but often all you care about is a particular property. If it's pupil size, dwell time, where they're looking, whatever, you can break it, instead of having to have that huge amount of data, you can kind of break it into smaller, easier to analyze chunks of data using that sort of binning analysis. And again, any of these which you do will also depend on this interest period. So you can do that for the whole, for all of it. You can select only to do this on interest areas or on the whole image. You can actually go in here and delete eye movements as well, if you really want to. You can actually delete particular eye. So if you have one that's way off, maybe that they were looking off the screen, you could actually delete that and it would be excluded from your analysis. Again, you're doing that based off of this. All that data is still kept in the original iLink data file. So you can always go, and anything you do, if you suddenly go, oh, shouldn't have done that, you can always go back and reopen a new file and redo it again from scratch. Or you can have, one set of data analysis for one particular aspect. Maybe you deal with the data differently in another, and you have a separate data viewer for that session. Or any point. So if I want to do something and I'm not sure how it's going to affect my results, I can always save it as another version and then go on from there. And then go, oh, I shouldn't have done that, and go back to that original data viewer session. There's no undo function, which is really annoying. So if you do make a mistake, you're stuck. That's why one of the biggest things you should do is save everything as you're going along. So as you keep on seeing this, I'm editing this. It keeps on prompting me, do you want to save before you do this? The reason is because at that point, at least you've got it somewhere you could go back to. So say, for example, if I delete a whole bunch of fixations by accident, I go, oh, I shouldn't have done that. I can just go File, Open, and reopen up that file again at the previous save point. So save as often as you can, and if you're about to make a major change, just change the file name a little bit. Call it beta, increment it by having an incremental number or something. Just a way in which you could then go back and get back to the original version of the results file. And then once you've got that data into Excel, or it's a text file, so you can open it up in Excel, SPSS, pretty much any package, then you can go and run your normal statistics. That's not a problem. Any questions? Yes.
What happens to the blinks?
Okay. So how are blinks dealt with? This is what happens by default. Is blinks are no eye movements, but they are.
Because eye track shows you blinks and you're just like there.
Yeah. So the blinks in this case here are excluded because there's no eye movement there. However, most eye tracking algorithms have problems with a blink because they actually sense them as a saccade. Because if you think about it, a saccade is a rapid eye movement. So you closing your eye rapidly and opening it generates a movement artifact, which most eye tracking algorithms actually consider to be a saccade. So if you go, and again, this is another way in which you can see how good your eye tracking analysis algorithm is you go look around a blink, see if it has a saccade before and after a blink. Because again, what will happen is you have in your eye tracking in that view file here. So let's see if we got an actual. Let's see if we go off here. Let's take this all off. Let's see if we have any blinks here. No, there's no blinks in this file. If there were a blink here, I could actually look at the acceleration before and after in that. What's the sample data? If there were a blink, I could actually look in this and see if there was a sudden acceleration, or if they thought it was an acceleration at the time of that blink. The iLink gives you an option of excluding saccades around the blink. So you can see, you can hear, I can apply a blink correction. I could tick this normally, and then I can exclude a duration immediately before and immediately after a blink. The rule of thumb, which has been published, is 100 milliseconds before and after a blink should be excluded. And so any fixation duration, any acceleration, any saccade, which is associated around that blink, is automatically removed from the analysis. So in terms of the eye tracking, you would have a blank. There would be a period where you would have no eye tracking data available.
Do you know if the
The which? I don't know. This is a new feature that's been around in Dataviewer for about a year now. Before that, you would have to do this by hand in your actual analysis file. I tell you that because I've done this many, many, many times. And this is a feature which has been requested a lot by the community. And again, iLink tend to be very good at listening. So this is now a new feature in the package. It's very useful because it lets you really then make sure that your saccades are really saccades and not related to other abnormal. We don't care about blinks and saccades normally in terms of the saccades which are associated with a blink. Number of blinks we do care about sometimes, especially if you want to look at startle effects. If you startle people tend to blink more frequently. So you can actually use that as an analysis type to look at the number of blinks during a trial. So if you show them something that's really nice, they'll kind of go, oh, look, and they'll stare at it really nicely. If you show them something that they're horrified about, they'll stop blinking because they're trying to stop the processing of the image as much as possible. Or they'll close their eyes. And you would have that information on the eye tracker. Again, the eyes in blink, if closed, there will be a marker in this view here, which will show you the duration of the blink. So if they close their eyes for 100 to 400 milliseconds, that's a normal blink. If they've had their eyes closed for about 2 minutes or 3 minutes, they either don't like what they're seeing or they've fallen asleep. But again, you can look at that in this view here. But again, the easiest way to see how any eye tracking analysis package analyzes the data is look at that view. Again, this view, yes, it's old, it's really difficult to interpret. It gives you an insight into how your eye tracking algorithm is really affecting your data or parsing the data. So if you're using something where you've never used this analysis software before, or you don't know how it works, which is how most eye tracking analysis we know, in fact, iLink, we know something about how their data analysis works in terms of how it defines a fixation and a saccade and the actual algorithm, because they published this data back in 1994. Most eye tracking companies, especially Tobii, do not tell you how they define what is a fixation and what is a saccade. And that is problematic, because sometimes the data could be telling you something, you believe it to be true, when in fact it's actually false. So again, every eye tracking package gives you an option to do this. Look at that. If you really don't trust it, or if it's a new package and you're assessing it, look at this sort of trial, this view of all the metrics, and you can toggle and see, well, how does it deal with saccade or blink? Because if I look at this and I see that it's a saccade before and after a blink, I know that there's a problem with the algorithm. However, if they give you a way of editing that, that's better. Or if you want to look at how defining fixations or saccades changes your results, this is where you can see it. Any other questions for today? Okay. Well,